I want to answer a question. Why should they put this constant to the antiderivative? What is very important thing? And to explain this importance, I'll make an example. For example, you have, I don't want to take very complicated function to calculate. I take some easy example. I want to calculate integration over, for example, sine x plus 3 dx. So I can use the property of the integration. When we have addition here, we can add two integral. Sine x dx plus 3 dx. Integration. Sine it is minus cosine x, and it gives sine if you calculate something. 3 gives you 3x, because 3x after differentiation gives 3, and you can differentiate this expression and you can have sine x plus 3 plus this constant, annoying constant. For example, I want to define antiderivative f of x for f of x. It is unknown, but I can have one extra question. Define f of x for f of x if so that f of 3 equal 5, for example. This is one extra condition. So this one antiderivative should be equal 5 if I put instead of x 3. So I can do it. Minus cosine of 3 plus 3 times 3 plus constant equal 5. So constant equal 5 plus cosine of 3 and plus minus 9. So the final view of this antiderivative of this particular condition is f of x equal minus cosine x plus 3 or times 6 plus 5 minus plus cosine of 3. I didn't fulfill this expression. 5 minus 9, it is minus 4, so it is minus 4 here. So it has this particular view. So this constant here is cosine of 3 minus 4, very particular. But what changes if you have here instead of f of 3 equal 5, another one? Define f of x if f of 7 equal minus 10. You will have a little bit another view of this antiderivative, and we can say here that antiderivative of this function f of x sine x plus 3 is not in one function. It's a familiar function which differ each other from other by this constant value. Today we work on the very last topic of this course. It's Riemann integral. And to make this work, I give you some simple examples, and your work will be very simple in your final term, because I think we don't have any time to drill it, and in very special circumstances and we can't consider the really complicated examples. So for the very beginning, it's enough to use this approach on some for example some elementary examples. For example, I want to calculate example this is e raised to power x function. The area of this shaded part from, for example, 2, 5 within the interval, the closed interval 2, 5. I want to know this area S. So S equal integration from 2 to 5. Instead of A and B here, I have to put these numbers. E raised to power x dx. So I know that e raised to power antiderivative of exponent is e raised to power x plus constant. I do not like c, if you don't mind. And here I use special denotation, this vertical line, and I put here 5 and 2. It's kind of, it makes more convenient real calculation, but you can avoid this one notation if you don't like it. And it is equal. And now I use this formula. I denote it here, that area equal AB f of x dx, or equal antiderivative at the point B minus antiderivative at the point A. And I have to take this 5, put into my result of integration, minus the same function at the point 2. And here you can notice here that you have c here minus c, and they kill each other. And we have e raised to power of 5 minus e raised to power 2. So here you have the answer. The area which is bound to this curve and limited by 2 and 5 points along the axis 6 has area e raised to power 5 minus e raised to power 2. Here you have an answer. You can notice that this c doesn't screw up this calculation because it's kind of self-eliminated.